Hello. Um, I'm back. So last time we learned how to do some matrix multiplication with our wormhole. Um, Today, we're going to continue learning about the hardware, but we're going to do something a little bit more complicated, or I guess more complicated in general, by trying to see if we can make an LLM from scratch, adapted from this book here by Sebastian Raschka. Um, he has a book called LLMs from Scratch, where he goes through building an LLM from scratch. And what I want to do is I want to start adapting some of this code that he has open source, along with other extras, and see if we can take that written for CPU. His stuff is in CPU, and actually translate that to using our wormhole for training an LLM from scratch. And so his repository here goes through building a GPT-2 architecture model from scratch using Python with very little libraries in general, just regular PyTorch. And yeah, it'll be fun. I recommend you read the book. I have read the book, and it's a staple of mine right now. And I'm still like reading and rereading because it's not like the easiest thing to understand in certain parts, and I'm still all new to this too. But it's helped me understand LLMs more, and it's I guess I would say I've come to appreciate what I'm looking at and working with day to day now. Okay, so what we're going to do is, okay, we're going to also need um, our documentation here, okay, and we're going to create a new notebook called, in this case, embeddings. That's like the first thing. So actually, I recommend you kind of go through the LMs from scratch repo, and kind of read some of the earlier notebooks, because he just goes through like tokenization and things like that. And the part where you really start to use Torch is the embedding layers. So we're going to adapt the embedding layers code, at least learn how that really works, and put it into using ttnn instead. So I'll just create a new notebook, and I'll save that like right away. So I can just call this embedding. Okay. And along the way, I'm going to try to, I guess, explore various features in ttnn. So I'll try to cram all this into just like conceptually building an LLM. Okay, so what are embeddings exactly? So embeddings are tensors, I guess, like matrices, that record information about like a context of a bunch of tokens. So in LLM world, substrings, these little individual substrings that get generated by the LLM, are called tokens, right? But in order for like an LLM to be able to figure out which next token to generate, it needs to actually understand the entire context, which is basically the input stream. And so it has to kind of look up or process through embeddings a bunch of math that allows it to determine, okay, well, I have this set of tokens available, right? Which one do I pick as the next one that follows? And the embeddings layers, they help with that. They're not necessarily the thing that will help generate the next token, but they are part of that process. So there's two types, right? There's the token embeddings, and that's basically a record of like the information necessary to take like a token and form a word in that context. So it kind of answers the question of what kind of word is this. And then the positional embedding layers is like the tensor that kind of records that information about the token and the relationship between the other tokens in context to the position for its kind of like context window. So it answers the question of where does this word sit in the sentence, essentially. Okay, and then when you combine the two, the token embeddings and the positional embeddings, you get what we call like an input embeddings. And then you use the embeddings themselves to build out your LLM system in general. So I'll walk through how to like compute all this, but you can really watch Sebastian's videos or like read his book or go through his notebooks to try and understand more. But for now, let's just focus on the coding part. Okay, so in GPT-2, did you know that there's actually only about 50,257 different tokens to essentially represent the entire English language, or be able to generate all the words in English language? So this space of tokens, this 50,000 some odd tokens, we can call that the vocab size. So we'll declare a variable called vocab size, and that's going to be 50,257 available tokens to use. And basically we want our dimensions, our output dimensions, for any type of forward pass we make on our embeddings layers to be just randomly 256 for now. I think in GPT-2 it's 1024, but given our system, we want it to run pretty fast. So let's take a smaller number in this case. Okay, so that easy part is done, and basically, I need to execute stuff. Okay, start my virtual environment. Okay, so that easy stuff is done. We have these two variables instantiated. We also need to import some libraries. In this case, we'll import Torch. Then we'll also import ttnn, which is the Tenstorrent NN library. And then we also need to write some code to do some data preparation, just like some sample text programs, so that we can process some input. In this case, Sebastian, he uses a short story called The Verdict, and so we'll do the same. I'll just straight up type up the code right now, and then we'll open up that file after it's downloaded. So then if you open Sebastian's repo with chapter 2, IPyNB, you'll see that he links to information about what is the verdict, right? So yeah, I think this is the entire story in its whole. But let's actually just write the code here to download it, and then put it into our repo. So basically copying, right? So we can just do this import here, and it looks like ttnn is good. So we'll do import os, import url lib dot request, and then we'll say if not os.path.exists. And let's actually create a data folder in the notebooks, okay, where our text files can be downloaded. So let's say if data / the verdict.txt, if it doesn't exist, what we want to do is we want to download it. So in this case, we can just copy and paste this URL here. Let's just kind of do that, and then copy, paste it. Okay. and then let's download it. So we can say, okay, our destination file path here is going to be, in this case, actually, why am I doing that? I'll just do data slash the verdict text. So that's where we're going to download that. And then we can do url lib dot request dot url retrieve. Okay. URL file path. Okay. So we'll only download it if the file doesn't exist. Right now, the file does not exist, so we can just execute that, and then we'll get the file here. So we'll have the text file. It's a verdict. Okay, so far so good. All right. So next, we want to be able to open up this text and process it in some way. So in this case here, we could just do the with open in Python. So we do with open data slash the verdict dot text. We'll open it in read mode, and then encoding will be UTF-8. Okay, as f. What we want to do is we'll just read it into a variable called raw text, and then let's actually print out the first 50 characters of that. Okay, so this is what we get after printing out the first 50 characters. Okay, so this is nothing to do with Tenstorrent hardware or embeddings right now. We're just kind of getting ourselves ready. Okay, so we also need to be able to create what we call a data loader to be able to load data, the data that we have, this verdict thing, right, into like batches. Right? So as we iterate through data, we get batches of this data of a certain context length. And for now, let's keep it small. Let's define a context length to be a 4, okay, 4 tokens. And then batch size, we're going to do 8 of these 4. So 8 like arrays, 8 tensors of these 4 tokens. Okay, so how do we actually process tokens? Like, how do we take these words and turn them into tokens? Well, we had to use a library that's available called TickToken, and that's actually the same like tokenizer. It's called tokenizer, right? It takes words and turns them into tokens, like numbers, essentially. I'm saying that a lot today, but let's take a look at what TickToken is. Okay, so TickToken. Is there a TickToken demo? Yeah, this TickToken demo. So basically we have, and this is 3.5. So that's a hello world. Okay, so basically TickToken, this is like a UI for that library. It understood that hello world is 2 tokens total, and those are the IDs of 15,339 and 1,917. And so the whole point of TickToken is to be able to encode text into these types of numbers and vice versa. So basically take in these numbers and decode them back into words. Okay? The approach to do this is using called byte pair encoding algorithm, which maybe one day we'll explore, but for now just kind of take it as it is. Okay, so we want to take all that text, translate into tokens, and then split them up into a specific context length. In this case, we'll define the context length to be 4, and then we'll also take a batch size of 8. So that's how many we're going to be taking at a time, or processing at a time. Okay, so next, we'll execute that. We're going to have to create a Python function or a class that's going to digest this data that we read, this raw text right here, into tokens, and then kind of organize them so that we can iterate through that data set as token, so as numbers. Okay, so before we do that, we have to install dependencies. We'll have to do a pip install TickToken just to install the TickToken library, and it's going to do that, and we'll get TickToken. So we're going to import a few things to create this class that will be our data set. So the thing that stores the batches of tokens that we're going to create. We're going to call this GPT dataset, and that's going to be an instance where we can just draw out data from it repeatedly. Okay, so in order to do that, we're going to have to import, first of all, Torch, because the dataset code, the library is inside Torch, or at least it's in, no, it's actually also in another library, or sub-library, sub-module called, I think it's called from Torch utils import import data set, yeah, and then data loader. Okay, and we'll also have to import tick token. So this is what we'll need to create our data set. All right, so easy enough. We can just do class GPT dataset. Let's just call that dataset, GPT dataset. That'll extend from the dataset class that we've imported. Maybe I should just type it better. Okay, so we need an init method. Okay, that will take in self, the raw text. We'll just call that txt. The tokenizer, which is the tick token tokenizer instance that we will be using to encode and decode tokens, and then a max length, which is basically the context length, and then the stride. So how many? Well, I guess that's also the context length too. So we pass. We're going to implement that later. And then we also need, since we're extending the dataset class, we need to also implement a len method. That's just basically self. So we also need to implement get item. So that's going to take in self naturally, and also the index, the current index, because it has to be iterable. Okay. So what do we need here in this data set? Well, we have text, raw text, and we also have a tokenizer. So we can just basically tokenize, and this may not be the best practice as your data set gets bigger, but what we can do is we can tokenize the entire data set in one go, like the entire raw text. And then we'll just kind of chunk it and put it into an array. So that's what we're going to do. So we can define a self.input IDs. Okay, so we need that in order to store, like, I guess if you kind of think about how LLMs work, let's say we have like some text here, hello world, I am, right? Well, so if the input is like this, what would be the output? What is it trying to predict? Well, it's trying to predict I am cool, right? So it'll predict hello world, I am cool, right? So this is basically input IDs. This is all the range of text that is going to be the inputs, and then the target IDs is going to look something like this, right? Like, given this string of text, what follows after it by one, right? If you shift it by one. So that's what we'll call input IDs. We'll also have target IDs, and then we'll actually tokenize everything straight up with the tokenizer .encode. We'll take in the raw text, and then we also have a special token that we need to consider. It's called the end of text token, and most, I guess, tokenizers recognize special tokens, and end of text is one of those things that help during training to have the LLM recognize that a specific chunk of text is done, right? So that is a special argument in the tokenizer encode called allowed special, and it just takes in like a set. We can just kind of just do this end of text. It's like a special character, special token. Okay, so then now we have all the token IDs. What we can do is we can actually iterate through those token IDs, creating those arrays, right? The context into individual, tensors. So the input IDs and target IDs are kind of like an array of tensors in this case. So we do for I in range, going from 0 all the way to the length of token IDs. We want to jump pretty much every stride number right here. And we don't want to go out of bounds, so we actually have to stop at our context length, which is going to be max length. And we do input chunk. So that's going to be for our input IDs. So we're going to slice away some portion of the token IDs and put that as the current input chunk. So we can do token IDs. That's going to be a slice from current I all the way to I plus the context length. Okay. And then we also want to take that target chunk, which is going to be one more over, right? So starting from the one more over. So if it had, in this case, for example, hello world I am, it's going to start now at world, right? So target chunk, it's going to be token IDs, I plus 1 in this case, all the way to I plus max length plus 1, because we need to also get that same number of tokens. So world I am, and coincidentally, one more over will lead to cool. So that's how this code is working. And then we want to append this input chunk and the target chunk. But before we do that, we actually had to convert that into tensor. So actually what we're appending is the tensor version of this array of numbers here. So we can just do self.input_IDs.append torch.tensor. It's going to be input chunk. And we do self.target_IDs.append. It's going to be torch.tensor target IDs. Target chunk, sorry. Chunk. Okay. So that's how we process the data set. Then length is just going to return back the length of all the input IDs. So we just return len self.input_IDs. So that's implemented. And then get item is going to return back a tuple of the input chunk and the target chunk at that current index. So we can do self.input_IDs is going to be IDX, and then self.target_IDs is going to be at that current index too. Okay, so we've defined this GPT data set. Okay, now next we need a helper to kind of initialize this and return back what we call a data loader. So given a data set, let's create a data loader out of it. Okay, so this data loader is going to be the one that initializes a tokenizer, initializes the GPT data set that we just created, and then initializes a data loader that will be used to be iterated over. So in this case here, in this new cell, we can just import, first of all, torch again. Actually, you know what, let's do it right here. Def create data loader. Okay, and this is going to be called by the outside world. Not we don't create the GPT dataset directly. Well, we need to call the create data loader as like a kind of like a factory method or a function that will give us back the data loader with the GPT dataset inside. So in this case, we do need text again. We need also the batch size, which we have defined already, but we'll just default to 4. Max length, in this case, is going to be our context length, and we'll just say 256 by default. And then stride, so we're going to jump every 128, okay, by default. We'll shuffle, that's an argument that you pass into the data loader. we'll see that's true. Drop last for dropout, or no, drop last. I forgot. I think that's to not consider the last chunk if it's uneven. Okay. And then I think that's it. Yeah. So we'll write that code. So first of all, we need a tokenizer so that we can pass in to the GPT dataset. So we can just do tick token dot get encoding. We want the GPT-2 version. We'll also prepare the dataset. We'll just initialize the GPT dataset class with the text, the tokenizer, the max length that we've gotten from the create data loader call, and then the stride. Okay. All right. Next, we just need to create the data loader. So data loader is going to be just data loader, right? And that's going to take in some arguments. We need a data set, which we have created, the GPT data set here. And then we also need a batch size, which is going to be whatever that was passed in through that call to create data loader. We also need to pass in the shuffle, right? Shuffle. We'll also need to pass in drop last. And then finally, we need to set num workers to 0 because we're working in a notebook. And then we'll just return this data loader. Okay, so we'll run that cell again. Everything looks good. Great. So at this point, we can write code that will actually take in now that raw text that we had up here loaded, right? This raw text, and then create that data loader out of it. So it's as simple as doing data loader equals create data loader with the raw text. Batch size is going to be whatever batch size we defined all the way up here. That's going to be 8. And then we're going to do max length. It's going to be the context length. In this case, it's 4. Stride is also going to be the same thing. It's going to be our context length. And then shuffle false. Okay, so let's clean that up a little bit. Let's add it like this. Okay, make it more readable, you know. Okay, so now we have our data loader. So next, data loader is an iterable, so we can just kind of draw out the first inputs and targets and see what's actually in there. So we can do data iter is going to create an iterator out of data loader, and then we can just draw out the first set of inputs and targets from it. So data iter, that's going to just call next on the data loader, and then we can actually print out what we get here. So we expect to see basically in inputs and targets, every element is going to be 4 tokens long, and it's going to be 8 of these stacked together. So if we run that, we'll see that that is true indeed. Something interesting to see is that, so this is going to be the inputs, and this is going to be the target. And this is like basically like a string of like 4 words, for example. We have 40, 367, 2885, 464. So like given this string here, what's predicted to come out of that will be, for example, in this targets here, 1807, right? So 367, which is 1 over, 2885, 1464, and then 1807. So that's what we're looking at here. Okay. So now that we have our data prep, we have like our inputs and targets, we can actually start creating our embedding layers. But so the thing is, it's really hard to when you're working with like something new. First of all, Torch is already new to me, and here I am trying to use ttnn. That's even more new to me. But I am better in Torch than I am in ttnn. So what I want to do first is just go through Sebastian's code and adapt. First do it in Torch, and then see what we can do to translate that into ttnn in this case. So the first thing we want to do is we want to create the embeddings layers. We're going to be creating the token embedding layer and then the positional embedding layers. And then we're going to combine those through summing them into input embeddings. And we'll see what that looks like. Okay? So yeah, so let's do this torch embeddings example. Okay, oops. This one is supposed to be, how do I turn this into markdown? It's M? Yeah. Ooh, that's large, but it's okay. All right, so it's fairly simple because Torch already gives us like an embedding module to create our embedding layers with. So in this case, we do token embedding layer. We do torch.nn.embedding, which is going to be that module. And we can pass in the vocab size and the output dimensions that we want. So it's going to be 50,257 by 256, or maybe dimensional tensor. And then what we want is we want to create a token embeddings. Okay, so we basically evaluate given our inputs that we've received here. Okay, so this eight tensor collection into our embeddings layer, so we can evaluate that with token embedding layer with the inputs passed in. Okay, and then let's see what that gives us. So token embeddings layer, or token embeddings, and that gives us basically, in this case, this also do the shape too. Okay, so that gives us an 8 by 4 by 256 tensor, right? So yeah, so basically here's how we look at this. Okay, every single element, which is going to be the most innermost dimension here, is going to be 256 elements long. And that's for every element in the current batch, which is going to be 4 elements long. Okay? And there's going to be 8 of these. Okay? 8 of these 4 elements that inside each of those 4 elements has 256 more elements. Okay? And when it comes to deciding what this is, the output dimensions is just basically like, kind of think of it as like the detail of how much you want the LLM to learn about a token. Okay, so I don't think there's like a hard set rule of it, at least from literature. So I think 256 is just like something to start out with. Anyway, next we can do positional embeddings. So I think I'm gonna call it positional embedding layer. And it's the same thing. This is torch.nn.embedding context length. And output dimensions again. Then we'll evaluate that and call it positional embeddings. Basically, taking the positional embedding layer, throwing, in this case, still the inputs to it. And let's actually see. Actually, no. It's supposed to be initialized from like 0 to your context length. I don't remember the reason why, but read the book. Here we're just trying to learn how to use ttnn. So that's going to be the context length. And so in order to see what that looks like, well, it's just basically outputting it here, positional embeddings layer. Oops. Positional embeddings. Let's do that again. Positional embeddings.shape. So it should be the same, right? So 4 by 256 is going to be what we're looking at here. So it's going to be initially a simple range of integers. I think it's like 1, 2, 3, 4, 5, and so on, all the way up to 256. And basically, it's going to be 4 of these. And yeah, so every element is going to gain that, right? And you're going to like stick it in. So input embeddings in this case is a combination of the two. So I think that's like point by point. So we have token embeddings plus positional embeddings, and let's see what we get here. Oops. Input embeddings dot shape. Okay. So see, it's still 8 by 4 by 256, which is the same thing as the token embeddings here. I think the positional just kind of encodes the context of like the significance of if this token is in like the first part of the sentence versus the last part or the middle part. Like, what does that even mean? So it's like a little extra information. So anyway, our task here is to translate this code, right, where we create the embeddings layer and pass it in with inputs. Same thing with positional, and then finally the input embeddings into ttnn. Okay, so that's like the goal. So in this case, I'm going to turn this into markdown, and then I'm going to say ttnn example. Okay, and that's what we're going to work on next. So the one thing with ttnn that I've noticed is that you have to write a lot more code to get to the same place. So just heads up warning, it's like we're gonna write a lot more code just to express the equivalent thing. I think that's just a skill issue on my part. I just need to get better at it. But for now, this is what I know of how I'm going to translate it. So bear with me. First things first, we have to initialize the device. So we give a device ID. In this case, why am I still marked down? Turn that into code. There we go. So we're gonna get our device ID, which is 0, because I only have one of these right here, device ID 0. And I am going to open the device. So I grab a handle, ttnn dot open device. Okay, is what I'm going to use with the device ID passed in. Okay. And at this point, if I execute it, I should see some logging, and if it says chip detection complete found, we're good. Okay. Next, we want to create those token embeddings. So I'm going to cheat a little. I'm going to reuse some of the inputs and the targets that we have. What's the cheat? That's how we're going to do it, right? I'm not going to create a data loader specifically for outputting ttnn tensors, is what I'm trying to say. We're going to use the inputs and the targets that we got from our data loader in torch form, right? At that point, it's in CPU memory. We're going to convert that into ttnn tensors, and then we're going to shoot them off to the device in 4 lines of code. So first things first, we have inputs and we have targets, right? So we can do inputs ttnn, which is going to be the ttnn tensors of the inputs torch tensors. So we do ttnn dot from torch. Okay, so we're going to convert those torch tensors inputs with d type. In this case, if you remember our tokens, let me see if we still have it. Yeah, our tokens are integers, right? So we actually had to use a specific data type by default. ttnn is going to want bfloat 16, but in this case, these aren't really floating points. These are integers, so we can do ttnn.uint 32. Okay. And then we have targets ttnn. So the ttnn tensor version of our targets, it's going to be ttnn.fromTorch targets dtype ttnn.uint32 again. So at this point, we have ttnn tensor versions of basically our inputs and our targets, at least the first batch of it, right? The first batch of 8. So look, it shows us a shape, it shows us the data type of the tensor, and then it also gives us the layout currently in row major, right? We'll talk about the whole tile layout and the row major layout afterwards, but this is what we have. So now we want to send these ttnn tensors to the device because we can't really do much with them if they're not on the device. The device means the wormhole card in our case here. So like before on our other notebook, we can just do inputs, ttnn dot to device given the inputs and also the device handle. We're going to send that ttnn tensor to the device, and then we'll get back that reference to it in device. And we'll do the same thing with targets too. Okay, so same thing. And I think at this point everything should still be the same. Okay? So, still the same. But now they are in the device memory. Okay. So the one thing about the embeddings layer in Torch is that I think I forgot to mention is that they are initially randomized because these are the numbers that during the training process will be adjusted, right? So internally, what's happening is that when you create the embeddings layer in Torch, it's initialized to like random weights. So when we had initially created the embeddings layer right there, these were just like random numbers. So we can just express the same thing in ttnn form. So we can define something called token embedding weights ttnn, right? ttnn.from torch. We are going to just create a random like number tensor. So torch.randn with a size, a vocab size, so 50,257, and then the output dimensions. Okay. Next, the parameter we need to pass in is the D type. And this time it's going to be bfloat 16 because these are all floating points. And then what we want to do now is we want to send those token embedding weights that we've generated to the device directly. So we could do token embedding weights ttnn, shoot that off to the device with ttnn.toDevice. With the token embeddings weights ttnn, like the original one in CPU memory, to the device, given that handle here, which we've already initialized all the way up here, just as a reminder. Okay. And let's see what that looks like. Cool. It's just random numbers, right? So we got to do these things need to be trained on. Okay. So now we have these weights, or these like random numbers so far. ttnn provides, I think, a helper. Let's look at this here. Search the docs, embedding. Yeah. ttnn embedding. Yeah, APIs embedding. Yeah. So basically, I think how this works is it's going to do this part of the torch. So ttnn embedding is a function, right? It's a function that does basically the same thing as this part of the torch example. So what we have just written is basically this part, right? Where we have created that initialized random weights tensor. But we need to do the evaluation based off of some given inputs in this case. And so we need this part here. So how do we express that in ttnn? This torch part where we do token embedding layer for pass with the inputs. How do we do that in ttnn? Well, with ttnn, we need to use this one here, this ttnn.embedding function. Basically, it takes in the input tensors and it takes in a weight tensor. And this weight tensor is going to be the tensor that we have just initialized here. Okay. Again, this has to be in device And then we also need to, yeah, it just has to be in device. So we already have those. We already have the ttnn for the inputs. We also have the ttnn tensors for the weights, which we created both on device. So at that point, it's pretty straightforward. What we can do is we can do token embeddings ttnn. So they're not weights anymore. They're going to be the evaluated tensor from those randomized weights with the inputs. Okay. ttnn.embedding is going to be our helper, and we're going to give it, in this case, what is it expecting? It's expecting inputs and weight. Okay, so we need to pass in inputs ttnn and also our token embeddings weights ttnn, and let's see what that looks like. Okay, boom, cool. So we just have a bunch of other random floating point numbers. Okay. So we just repeat the same thing technically with the positional embeddings. Okay. Positional embeddings, I think it's easier because it's just a range, like increasing range of things, of numbers, right? That's also considered that it has to be uint32. So we could just do positional inputs as ttnn.arange. So ttnn does provide a helper that does the same thing. Okay, we should say ttnn. Okay. End is going to be how far do we want to go? That's going to be the context length. And then dtype is going to be ttnn.uint32. Okay, and then positional inputs ttnn has to be sent to the device. To device, positional inputs ttnn to the device. Okay, and let's just output that. Good. Okay, so we have basically an integer tensor in the device now. So now that we have those positional inputs, let's create those weights for the positional embeddings. So positional embeddings weights. Positional embeddings weights. Okay. Should I do ttnn? We should. We can say, well, we already have that. I guess from. No, we have to randomly initialize it from torch again. Okay, ttnn.from torch, because I don't think. Let's see, does ttnn provide rand n? But what I'm trying to say is that we need to use torch to build a random matrix, and I don't think so. Let's see here, APIs, shape, yeah. Yeah, let's see. APIs, operations. Here we go. Let's search for rand. Yeah, it doesn't. There's no rand. It looks like. Yeah. So we'll create from torch, and then we'll do a from torch, like I am doing right now. So we do from torch dot rand n going to context length with output dimension. So we're going to do a 4 by 256 in this case. The type is going to be ttnn.bfloat16. Okay, and then we are going to positional embeddings weights ttnn, send it to the device. Okay. Was it positional embeddings weights ttnn to the device, and then we'll output that like so. Okay. Does that look right? It does, I guess. Yeah. Oh, wait. No. Positional embeddings weights ttnn. Let's try it again. Okay, good. The shape was not right. Okay. Alrighty. So, again, we want to take those positional inputs, then the position, and evaluate that against, well, yeah, with the positional embeddings weights. Okay, so similar to, in this case here, this code. We want to emulate this code here. So, and notice how we did a range from 0, 1, 2, 3, right, as that input. So we created that. We created that here. So we have to pass this into this thing here with the ttnn embeddings function. So it'll be in positional embeddings ttnn equals to ttnn dot embedding, and given the positional inputs ttnn, and also the positional weights, embedding weights ttnn, we'll create that layer and then see what we get out of it. Positional embeddings ttnn. I need to name things better. Okay, so far so good. It looks like we're emulating things correctly now. Okay. Now, the thing is that we're not quite done with positional embeddings ttnn tensor. We had to kind of reshape this thing so that it can be added directly to the input token embeddings, or so it can be added with the token embeddings to be the input embeddings, right? Now, we can't just simply add it like we did in Torch before, because in Torch we can do that, but in our Tenstorrent hardware, what's happening is that it has to be point-wise addition. Like, so the problem is that our token embeddings has a shape of 8x4 by 256 at the moment, but our position embeddings is only a shape of 4 by 256, right? And the Tenstorrent hardware operates differently in the sense that the tensors that you're adding have to like match up perfectly. I don't know how else to describe that, but what we had to do is we had to just repeat this thing 8 times basically to create that same shape. So then we can just like add them together into the input embeddings. So we do a positional embeddings ttnn, which is like reuse it, right? And then we could do ttnn.reshape positional embeddings ttnn, and then provide that with the new shape. In this case, we want to create basically one element of 4 by 256 in this case. Oops, we should use variables. Okay? And if you really want to know what that API looks like, it's scroll up. Is it reshape? Right there, ttnn reshape. It's just preview. So, yeah, it just takes in, what is it? It takes in the input tensor and then the new shape. Basically, that's what we're doing. We're just reshaping the input tensor, which is going to be the positional embeddings ttnn, and we're going to reshape it to a 1 by 4 by 256. And then what we're going to do after that is we're going to just repeat that 8 times. Okay, my mouse is going pretty crazy for it right now. I'm using a trackball, so it's just for some reason I don't know. All right, we'll use the keyboard. Okay, so we've done that. We've reshaped it. Now we need to repeat that, and the API for that is going to be called repeat. No, I think it's repeat interleave. Yeah, repeats elements of a tensor given the dimension. Okay, so that's how many times you want to repeat it, which is easier to use. So input tensor and the number of times you want to repeat it. Okay, so positional, we'll just reassign positional embeddings ttnn is going to be ttnn dot repeat interleave. Typo. Repeat interleave, positional embeddings ttnn. How many times we want to repeat? Well, the batch size, which is 8. And then at which dimension? 0. So the first one. And then let's see what that looks like now. Positional embeddings ttnn. Okay, cool. So we've reshaped this thing to now be 8 by 4 by 256. Okay? So, yeah. Now we just need to add it together. Okay? And that's pretty easy. That's going to be input embeddings ttnn is going to be ttnn.add. So that's going to be that pointwise add, like I said, element for element, since they're the same dimensions anyway. So okay. So now here's the thing. Remember that all our tensors at the moment they are in row major format, right? So something about these operations you should know is that since they're going to be operated on the device, they have to be in tiled layout. So it says here, like, supported D-types, layouts, and ranks. We can only add tensors that are either bfloat 16, bfloat 8b, and 32, 16, and they have to be tiled, right? So what we want to do is we want to convert our embeddings, both our embeddings to be tiled, right? So what we can do is we can just do token embeddings ttnn. We could just do ttnn dot to layout. I think that's okay. That's the layout. So that converts row to tile, tile to row, vice versa. So it just takes in the tensor and then the layout we want, and then optional D type, and then the device that you want to tile to. So token embeddings ttnn layout is going to be ttnn.tile layout. Device is going to be just be the device. And it will do the same thing for the positional embeddings, ttnn. Same thing, ttnn.to layout. We'll have the positional embeddings ttnn. Layout is going to be ttnn.tile layout. And then device. Okay, so pass those in. We're going to add these two tensors, and we should get the input embeddings ttnn and see what that gives us. Cool. So now we end up with still again the shape of 8 by 4 by 256, and we have a bunch of random numbers, seemingly random numbers, because right now they're just random. They need to be trained. Okay. Yeah, so I think that's it. I think that's all I want to do for today. I think after that it's too much. This video is kind of getting long. So yeah, let's kind of clean up. We'll close the device. We don't want to leave our device hanging. That's it. Let's actually just comment or something. So let's add some markdown. Ooh, not there. How do I do it up here? Let's see here. Insert cell above. Oh, Control Shift Enter is how we would do that above, and then we'll convert that to markdown, and we'll say embeddings example with ttn. Okay, and then we'll just say, okay, first define some variables that we will be using. Okay, and then import torch and ttnn, and then libraries. If ttnn is successfully imported, you'll see some logging related to config. Okay, and then what we want to do here is this code. Okay, so let's actually create a new section. Prepare dataset. Okay. we will use the short story, the verdict.txt, as our sample data set. Download the text to data/the-verdict.txt. Okay, this is a good summary, right? We're doing this. Okay, this one here is define the context length and batch size to be used throughout the notebook. The batch size is the number of tensors that we get total for each iteration of our data loader. Okay, and then pip install. Let's see, pip install tick token if not already in the system. Okay, and then here we will create our custom data loader. So creating custom data loader. This data loader will store our inputs and targets tensors. Okay, they are still in torch form. Okay. Oh, and then we should basically create our data loader through the create data loader call. So we can create a custom, or say initialize the data loader using the create data loader function call. Okay. Then finally, torch embeddings example. Okay. It is easier to do this exercise first using torch, and then we'll adapt and rewrite it using ttnn to the best of our ability. Okay? Yeah. And then finally, let's go to ttn example. Let's rewrite everything using ttnn, but first let's open a device by using open device and storing the handle. Okay. And I guess everything else is like, you can just watch the video. There's a lot of stuff. But yeah, we'll do more next time. Thanks.